Thyristor chopper circuits. A thyristor chopper circuit uses a fast turn of thyristor as a switch and requires a commutation circuitry to turn it off. There, we encounter some problems of minimum turn-on time limit, high frequency operation, and reliable operation. Due to this, the application of thyristor chopper circuits are limited to high power level like a traction motor control. We have two types, that is impulse commutation chopper. Second one, resonant pulse choppers. In impulse, we have two combinations, that is using two thyristors, one diode, and three thyristors. Let us discuss the first one, that is impulse commutated chopper, in detail. The impulse commutated chopper is a very simple circuit with two thyristors, T1 and T2, and a diode D1, where T1 is the main thyristor and T2 is the commutator circuitry thyristor, and D1 LM and C is the commutation capacitor, LS is the source inductor, and DM is the freewheeling diode connected to the load. The operation of impulse commutator chopper can be divided into 5 modes. Mode 1 is resonant recovery current mode. Second mode is commutation mode. Third mode is overcharging mode. Fourth mode, undercharging mode. Fifth one, freewheeling mode. So mode 1 begins with the T1 is fired and the load is connected to the source. Then the load current IA or IM is equals to IS. The commutation capacitor C reverses its charging through the resonant reversing circuit formed by the T1, D1, LM and C. The resonant current IR is given by VC square root of C by LM sine omega m of t. Let this be equation number 1, where omega m equals to 1 divided by square root of LMC. Now, the peak value of resonant reversal current IPR equals to VC square root of C by LM, as the sine omega t maximum value is 1. Let this be equation number 2. Now, the capacitor voltage VC of t is given by VC cos omega m t. Let this be equation number 3. After time t equals to TR, which equals to pi square root of Lm of C, the capacitor voltage is reversed to minus Vc. This is called commutation readiness of the chopper. Resonant reverse time t equals to TR, let it be. In that time, the voltage of the capacitor is going to reverse from Vc to minus Vc. Since the source is connected to load, the load current is going to rise from minimum value. Thyristor 1 is turned on, so voltage across the thyristor T1 is 0. The current across the thyristor is going to rise from Im to a peak value and reduces to Im. Current in the capacitor will be negative minus Ip during the time TR, and the output voltage is equals to the input voltage Vs. So at the instant of TR, the capacitor is ready for commutation, but the thyristor T1 turn on time is up to kT. So the voltage will remain at Vc up to kT. The output voltage will remain Vs up to kT. Voltage across the thyristor T1 will be 0 up to kT. The current through the thyristor T1 will remain at Im until the T on time, and the current through the IC will remain 0 until the T on time. By the T on time, the output current will increase from the minimum value to the maximum value. Mode 2, the commutation mode. At the time equals to kT, thyristor T2 is fired. The voltage of the capacitor is already reversed during the TR time, so the voltage of the capacitor is minus Vc. So that reverse voltage of Vc is applied across the thyristor T1. It is turned off. The capacitor is going to discharge through the load from minus Vc to 0, and this discharge time is called available circuit turn off time, T off. As the current Im through the load is supplied by the capacitor, Im equals to C dV by dt, where this V is falling from minus Vc to 0, C dVc by dt. Then this equals to C Vc is the change in the voltage for the time t off. Time t off is given by C Vc by Im. Let this be equation number 4. During the turn of time, the capacitor voltage falls from minus Vc to 0. At the time, the output current equals to Im supplied by the capacitor. At the same time of t off, the output voltage will rise to Vs plus Vc, as Vs and Vc is going to supply the load voltage. The voltage across the thyristor T1 is going to fall negative, which is the value of Vx. Current through the thyristor T1 will be 0 as it is turned off. Current across the capacitor will be equal to Im. Im is the peak load current. Now, the circuit turn off time T off should be greater than the thyristor turn off time TQ. Turn off time varies with the load current and must be designed for the worst case, which occurs at maximum value of the load current and minimum value of the capacitor voltage. The time required for the capacitor to recharge back from the supply voltage is called recharging time. It will be given by the Im equals to C dV by dt, that equals to C of 2 Vs divided by time is recharging time T d. So Im equals to C of the change in the voltage is Vs divided by Td. Now Td equals to CVs divided by Im. Let this equation number 5. The total commutation time Tc is given by T off plus Td. Let this equation number 6. After T off, it should be Td, where the capacitor is going to reach Vs and the Im will remain constant and the voltage across the thyristor T1 max. The current through the T1 will remain 0. The mode 3 operation, so overcharging of the commutation capacitor C. Mode 3 begins when the freewheeling diode Dm starts conducting and the load current decays. The energy stored in the source inductor Ls is transferred to the capacitor. Now the current Is at T equals to the maximum current Im flowing through it cos omega s T, where omega s equals to 1 divided by square root of Ls is in connection, so Ls of C. Let this be equation number 7. The instantaneous capacitor voltage Vc at time t is given by the Vs plus overcharging is up to Im square root of Ls by C sine omega s of t. Let this be equation number 8. After t equals to Ts, that equals to 0.5 pi square root of Lsc, this overcharging current becomes 0 and the capacitor is recharged to a value of Vx that equals to Vs plus del V. This is equation number 9, where del V and Vx are the over voltage and peak voltage of the commutation capacitor respectively. Now the overcharging voltage delta V is given by, when you compare the equations 8 and 9, Vs equals to Vs, then delta V equals to Im square root of Ls divided by C. This is the peak value, equation number 10, during which the capacitor voltage is going to reach the peak value of Vx. This is Ts value. By the end of commutation, the output voltage is going to reach 0. It will stay at 0 and Vt is going to rise to Vx. It1 will be 0 and Ic will be at Im until Tc, commutation time. After commutation time, it starts decreasing to minimum value. Output voltage is going to decay in this time. So mode 4 is the undercharging of the capacitor C, begins when the overcharging is complete and the load current continues to decay. This mode exists due to the diode D1 because it allows the resonant oscillations in mode 3 to continue through the circuit from Dm, D1, Lm and C to the supply. This will undercharge the commutation capacitor C, and the undercharging current through the capacitor C is given by Ic of t equals to minus delta V square root of C divided by, both the inductors are involved, so Ls plus Lm sine omega u of t. Let this be question number 11, where omega u is given by 1 divided by square root of c by ls plus lm. The commutation capacitor voltage Vc of t is given by the Vx minus delta V of 1 minus cos omega u of t. After t equals to Tu, the undercharging current becomes 0. This is Tu period, is in between these two, and diode D1 stops conducting. Now the available commutation voltage of the capacitor Vc equals to Vx minus 2 delta V, which equals to Vs minus delta V. Will this be equation 12? Then this be 13. If there is no overcharging, there will not be any undercharging. Now the Vc comes back and Vs will be still at of 0. V0 is still 0. Vt1 will comes back to Vc. Current I0 will be decreasing. So mode 5 begins when the commutation process is completed, and the load current continues to decay through the freewheeling diode Dm. So this is freewheeling mode. This mode ends when the main thyristor is refired at the beginning of next cycle, or else this will end at t equals to capital T. Output current is going to decay. The capacitor voltage is going to stay at Vc equals to Vs minus delta V. The output voltage will be 0 until here. Voltage across the T1 will be Vc until the T. Current of the capacitor will be 0. The next cycle begins. Capacitor reduces to minus Vc, and this again starts building, and this again goes to Vs value, and this again comes to 0 value, and the current thyristor goes to Im and rises to Ip and falls. Current through the capacitor will be decreased and goes to 0, negative Ip. This is positive Ip, and this value is 0 here, and this value is Vs here, and this value is reversed here, that is minus Vc, and this starts increasing. Now the average output voltage of the chopper is given by the V0 is equals to the total time, that is 0 to t, so 1 by t of, if you observe the output voltage waveform from 0 to t on, the output voltage is Vs up to kt plus, this is a right angle triangle, it reached Vs plus Vc in the time t off plus td, that is nothing but tc divided by 2. Let it be equation number 14. If k equals to 0 in the above equation, V0 at k equals to 0 equals to tc divided by capital T Vs plus Vc by 2. 1 by t is nothing but f is the switching frequency of tc, half of the time, so 0.5 of Vs plus Vc. You can write this V0 at k equals to 0 equals to 0.5 times of f tc of Vs plus Vc. Let this be question number 15. This limits the minimum output voltage of the chopper. Now the thyristor T1 must be on for a minimum time of Tr, resonant reversing time, which equals to pi square root of Lm of C, to allow the charge reversal of the capacitor, and Tr is fixed for a particular circuit in design. Therefore, the minimum duty cycle and the minimum output voltage are also set. So Tr equals to K minimum of capital T, that equals to pi square root of Lm of C. Question number 16. Minimum duty cycle, that is K minimum, is equals to Tr is Tr divided by capital T, that equals to Trf, which you can write as pi f of square root of Lm of C. This is equation number 17. The minimum average output voltage, that is V0 of minimum, is equals to K minimum Vs plus 0.5 f T C of Vs plus Vc. Substitute the value of K minimum from the equation number 17 and take out the frequency as common, f of Vs Tr plus 0.5 Tc of Vs plus Vc. Let this be question number 18. So the minimum output voltage V0 minimum can be derived by controlling the chopping frequency, that is f. Normally, V naught minimum is also a fixed value for particular design. Now, the maximum value of the duty cycle is also limited in order to allow the commutation capacitor to discharge and recharge. So, the maximum value of the duty cycle K max of T equals to the total time minus the commutation time Tc minus overcharging time Ts, undercharging time Tu. Maximum duty cycle K max equals to this whole term divided by T. So 1 minus of Tc plus Ts plus Tu divided by capital T. This is equation number 19. The maximum output voltage, that is V naught of max, equals to K max Vs plus 0.5 Tc F of Vs plus Vc. As the T1 carries resonant reverse current, thereby increasing its peak current rating and limiting the minimum output voltage. The discharging and charging time of commutation capacitor are dependent on the load current, and this limits the high frequency operation, especially at low load current. The T off, that is available turn off time, and commutation time Tc and or voltage delta V depends on Im instead of Ia. These are the limitations, and there are some fixed values that need to be addressed for the betterment of Thyristor choppers. An ideal Thyristor chopper should not have limits like the minimum on time, maximum on time, minimum output voltage, maximum chopping frequency. The turn off time should be independent of load current. At high frequencies, the load ripple current and the supply harmonic current become smaller. In addition, the size of the input filter is reduced. So this is regarding the impulse commutated choppers in detail. Like, share, subscribe and comment.